Good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the topic on summation convention, which is also known as Einstein notation. So let's get into it. So in this lecture today, we'll be talking about the summation convention. I'll be defining that and taking you through lots of examples which will help you understand the convention in detail. It's very important to understand when we cannot apply this rule so that you get comfortable with the use of tensors. So in the last lecture, towards the end, we had briefly written that a vector v can be written as, in its expanded form, as the sum of the three components, which in using the sum notation can be written as sum I going from 1 to 3 vi ei. So let me draw the three-dimensional Cartesian coordinate axis O x1 x2 x3, where e1, e2 and e3 are the unit vectors. So now using Einstein's notation, which is also called the summation convention in texts, we will learn how to simplify this expression. Let us write the definition of the rule first. So the rule says that if an index in a mathematical term appears exactly twice, so let's underline the key aspects here. So first, it's an index in a mathematical term if it appears exactly twice, and that's very important, then a summation is implied over it. Okay, so what that means is that let's look at the term we just talked about. So the index in this case is I. So if I was to write this expression VIEI, so let's test the summation convention on this expression. So where's the index? The index is I. So I'll call this, this is called the index. Does this appear exactly twice? The answer is yes. Does it appear in a mathematical term? So yes, this is a mathematical term. So VIEI is a mathematical term. So if the index I in this mathematical term is appearing exactly twice, then from the summation convention, summation is implied over it. So what that means is, it implies that there is a sum on the index I, where the index I goes from 1 to 3, because we live in a three-dimensional world, VI, EI. So this is what the Einstein notation or the summation convention says. So as I mentioned last time, this is a notation. We have chosen to use it, so we are applying that through the definition. So let's learn or understand the notation through a few more examples today. So this was the first example that we used to understand the notation. So let's take another example. So the term we have is UIVI. So let's write expand UIVI. So let's check through the definition. So the definition of the Einstein notation or summation convention says that if an index in a mathematical term appears exactly twice, so in this case, the index we have is I, which appears exactly twice in this mathematical term, So that means that summation is implied over it. So I can write this as sum I going from 1 to 3 ui vi. All right, so this expands to u1 v1 plus u2 v2 plus u3 v3. And as you may already have guessed that this is nothing but the dot product of the two vectors u and v. So u and v are vectors because we notice that u has one index and v has one index. So they are both vectors, and this quantity ui vi actually denotes the indicial notation representation of the dot products between u and v. We'll go into details about vector and tensor products later, but this is just for noting down. Now remember that this is a notation. It's not a rule of mathematics where we write ui vi as an expanded form. It is just making our life easy. It's making it convenient, so we choose to use it. So in this course, as I mentioned last time, we will be using the summation convention or the Einstein notation. So whatever expressions we write, if we have an index appearing exactly twice in a mathematical term, then a summation will be implied over it. It's not a choice whether we want to apply a summation or not. Summation is implied over it. So ui vi in our case, or in the case where this convention is used, will always expand to u1 v1 plus u2 v2 plus u3 v3. So the index that we have used here, the index I that we used here, is actually called a dummy index. Now the meaning of the word dummy means not real. So the index I does not have a meaning by itself. So let's also write there's no meaning. So what that basically says is that if you have the expression ui vi and you expand that, which basically expands to u1 v1 plus u2 v2 plus u3 v3. So the index I did not have any real significance here. It was purely a dummy index which ultimately expanded to something in an expanded form. So from that logic, I can also write uivi as ujvj, because from the Einstein's notation or the summation convention, a summation is implied over it. And when I apply a summation from j going from 1 to 3, it expands to the same form, this. Or I could use an index k, so it becomes uk vk. All right. So the indices I, j, or k in these expressions I've written have no meaning by themselves. So they are called dummy indices. We also use the word repeated index. So the index I is repeated here. So it's called repeated index. So we will be using the word dummy or repeated often in this course. So to understand this notation properly, I suggest to you that you think of different cases. Okay? Just imagine what if this happens, what if that happens. So try to think of all the cases possible with different kinds of expressions, try to think of exceptions, and this is how, through reasoning and arguments, you will learn how to use this notation. So I'll be giving you examples, definitely a lot of examples today, but I urge you to please think about different cases yourself, which will help you a lot to understand this notation. So let's study a few more examples. Right, so is UIVI the same as VIUI? So I request you to please pause this video and think about it. Right, so I'm sure you have thought about it by now. So let's check it out. So let's see the right hand side. So VIUI is the sum I going from 1 to 3 VIUI, because from the summation convention we can write there's a summation implied over the index I, because I is a repeated or a dummy index here. So this expands to V1 U1 plus V2 U2 plus V3 U3. So V1 and U1 and V2 U2 and V3 and U3, they're all scalars here. Remember, scalars are zeroth order tensors that only require magnitude to describe them. So here V1, it's a component of a vector, so which is a scalar. So I can change the order. So I can write V1 times U1 as U1 times V1. Similarly, the second mathematical term becomes U2 times V2, and the third becomes U3 times V3. So this is nothing but summation I going from 1 to 3 Ui Vi, and applying the summation convention again in reverse. So this becomes Ui Vi. And remember, I is a dummy index. I could have written Uj, Vj, doesn't matter. So the answer to this is yes, Ui Vi is the same as Vi Ui. So let's look at more examples. So in this case, the mathematical term that we have is Ui Vi Wi. So the question is, what does this expand to using the Einstein notation if it expands to anything? So let's again check the definition. So the definition of Einstein notation or summation convention says that if an index appears exactly twice in a mathematical term. So the index we have in this case is just an index I. Does it appear exactly twice? And the answer is no. It does not appear exactly. It's actually appearing thrice. So I appears so the rule cannot be applied. In fact, because we are using the Einstein notation, we are not allowed to use an index more than 2 times in our mathematical terms. So that's a very important point. So we'll write it down. Right? So it can only appear either once, that will be when it's called a free index. I will talk about it later in the lecture today. And it can appear twice, in which case it is called a dummy index, where it expands using the summation convention rule. But it cannot be applied, or it cannot appear more than twice, because it creates confusion. Because if it appears 3 times, like in this case, if I just look at this part, it might seem that it can expand to the sum, but then there's an I left. Or if we apply this to VIWI, then there's a confusion. So for that reason, we are not allowed to use an index more than 2 times in a mathematical term in if we choose to use this notation, which we have chosen in this text. As a next example, so in this example, we have 2 terms in the expression, and we have to expand this using the summation convention. So this is the first term, and this is the second term. So I'll write it down that we have 2 terms in the expression. So let's go back to the definition of the summation convention. So if an index appears exactly twice in a mathematical term, so remember this whole thing is a mathematical expression or an algebraic expression, but we are looking for terms for the application of the summation convention. So in this case, we can individually apply the Einstein notation or the summation convention to the two terms. So in the first term, when we apply the summation convention, this expands to a summation I going from 1 to 3 ui vi, and the second term expands to summation I going from 1 to 3 vi wi. So now we can expand this. So this is the expanded form of the expression in this example. So what you should not confuse here is that the index I appears 4 times, because that is not the case. Remember, we are always talking about mathematical terms for the application of the summation convention. So in this case, the index I appears exactly twice in each mathematical term, so the summation convention can be applied. Okay. So just remember that I does not appear 4 times in the term, it only appears twice in the term. So as I said, that these are the kind of examples we're looking for improving our understanding of the summation convention. Let's now look at another example. So we have one mathematical term here, and we'll see if we can apply the summation convention here. So if I look at the index I, it appears exactly twice. In this mathematical term, and similarly the index j, this also appears exactly twice. So I can apply the summation convention, although I'll have to apply it individually over I and j in the same term. So first let's apply it over I. And then, because it's multiplied with the wj, so we'll apply the summation over j. And then now we can expand the whole expression. So this is the expanded expression. I won't multiply the terms because we'll have u1 v1 multiplied to all these three terms. So there'll be a total of 3 times 3, 9 mathematical terms in this algebraic expression. But I'm sure you can do it yourself. So we can see that using this summation convention or the Einstein notation, it makes things quite compact in terms of presentation. And that was exactly the reason that Einstein chose to use this notation in his relativity paper. Let's ask us a question. So the question asks whether UJVJ times WIEI is the same as UIVI WJEJ. And by now, I'm sure you have started to figure out that they're exactly the same, because the indices I and j are dummy indices. So it doesn't matter whether I swap them in the expression, because we always have to think of what the expression will look like once we expand it completely. And we can easily see that since j and I are dummy indices, I can do it in steps, in fact, to show you that in the LHS, let's do it. So you have uj vj times wi ei. So what I'll do is I'll replace j with k, because remember it's simply a dummy index. So it doesn't matter whether I write uj vj or I write uk vk. So that they are exactly the same. And then what I'll do is I will replace I with the j here, because I can do that. J is I is a dummy index, so say so is j. So wj ej, and in the next step, since I is gone, I can replace k with an I, because it'll still work. And you can see that this is equal to the right hand side. So this clearly shows us that these two expressions, or these two terms, are exactly the same. So we can swap the dummy indices because of the nature that they are dummy or repeated. So now let's try to apply or test this notation for tensors of higher order. So till now we've been working with vectors, but why not apply it to second order tensors? So the problem says that for a second order tensor sigma ij, expand sigma ii. So first let us check whether our definition of the summation convention will work here. The definition says that if an index appears exactly twice in a mathematical term, so is sigma ii, is it a mathematical term? Well, yes, it's a mathematical term. So we can check for the repeated index, and also the index I appears exactly twice. So if an index appears exactly twice in a mathematical term, a summation is implied over it. So what that means is that this is equal to sum I going from 1 to 3 sigma ii, which can further be expanded to sigma 1 1 plus sigma 2 2 plus sigma 3 3. So if you look at sigma as a matrix, the kind of representation we had shown yesterday or in the last lecture, you can easily see that this is the sum of diagonals of the sigma matrix. In fact, this has a name. It's a very important quantity. As we'll see later in the course, it's an important quantity mathematically as well as from a physical point of view in continuum mechanics. This is called, I'll write in bold, it's called the trace of the tensor sigma ij. So sigma ii is the trace of sigma ij, which is basically the sum of the three diagonal terms of the tensor. So if I want to write the trace, I can simply write sigma ii. Now, is that equal to sigma jj? Well, the answer is yes, because it doesn't matter whether I use j or an I or a k, they're all dummy indices. They will expand to the same expression eventually. Right? So we have learned now that the summation convention can be applied to the indices in a second order or higher order tensors as well. So let's look at a slightly more complicated term which involves a vector and a tensor. So vi sigma ij. So we have to expand this. So again, we'll do it quickly now. So we have a mathematical term where the index I is an index which appears exactly twice. So this means that summation is implied over it, and when I expand the expression, I get a v1 sigma 1j plus v2 sigma 2j plus V3 sigma 3j. So that's the expanded form of this expression, which only has one term in this case. So you can see that the final expanded expression has still got a j in it, and there's nothing we can do about j because j is appearing exactly once in each mathematical term, and which is called a free index. So j is a free index here, so it can take any value 1, 2 or 3. It does not expand here. So if you were writing this expression vi sigma ij, uh, it won't be complete until you specify the value of j. Otherwise it stays general in the sense that you will have to substitute a value of j for it to have a meaning from a physical point of view. So j can take a value 1, 2 or 3. There's no expansion happening over j because j is a free index, not a dummy index. So I'll summarize. An index can either be free if it appears exactly once in a mathematical term. I'm not writing that again and again, and it's repeated or dummy if it appears exactly twice. So let's take another example, and this is going to be the last example in this lecture. So let's take a higher order tensor Cijk. So Cijk is a third order tensor, and we have to expand the term Ciji. Now we can see that it's a mathematical term like you had in sigma ii. This is a term. It has an index I that appears exactly twice. So we can write it as a sum of I going from 1 to 3, Ciji, which becomes C1j1 plus C2j2 plus C3j3. And j is a free index. So depending on the value of j that you have in the expression that was given to be expanded, the value of j will be replaced in this. Otherwise, you can keep it general in the in j. So what we have seen is that the indices can repeat in different elements like we had previously in this case, where v has an index I and sigma has an index I. So the repeated index is appearing in different quantities, or it can appear as subscripts in the same tensor, which is happening here, or if that happened in sigma ii. So that is going to be the end of this lecture. I hope you have been able to understand the summation convention, and as I said, please try examples, think of situations where you could potentially break this notation, and this is what will give you the a strong understanding of this notation. It's a very important notation, as we'll see when we apply further algebraic and calculus based operations using this notation. So one has to get a good hold over it eventually for an understanding of continuum mechanics. So let's summarize today's lecture. So we learned about the summation convention. We did a lot of examples, and we learned about the difference between two types of indices. One is called the free index and the other is called a repeated or a dummy index. So in the next lecture, we will start applying various vector and tensorial operations using this indicial notation with the summation convention in place. And we'll also in the process define some important identities which will help us simplify mathematical expressions involving tensors for writing more compact and uh, more richer notations in continuum mechanics. So let's do a quick concept check for this lecture. So the first problem says, is ui vi plus vj wj the same as ui vi plus vi wi? Right. So think about it, whether they are the same. And the second problem, it says that we have to expand this term, which is vi wj times sigma ij. So please always go back to the definition if you have any confusion. In fact, I suggest in the beginning you should go to definition of summation convention to ensure that you have a strong understanding and there is no confusion as such. So thank you, and I'll see you in the next lecture.